Hello and welcome to this video on performing composition on linear transformations. Now, for those of you who have taken either a pre-calculus class or algebra class before, calculus even, you've seen this, most likely you've seen the composition of functions of real variables. This is very similar to that, has basically the same definition, only we're going to be working with specifically linear transformations here. So I'm going to start the video. I'm going to start off by defining what is the composition of linear transformations. What does it mean to do that, to compose linear transformations? And I have a couple examples where I'm given a pair of linear transformations and asked to compose them or find their composition in either order and evaluate them. Then at the end of the video, the latter half, I talk about when is a composition of two functions guaranteed to be one-to-one, and when is a composition of two transformations, when is it guaranteed to be onto? And also some things to look out for when talking about the one-to-one-ness or injectiveness of a composite transformation, and also some things to look out for and be careful of when talking about the onto-ness or surjectiveness of a composite transformation. Okay, so on the first page here, just defining what is the composition of two linear transformations. So suppose we have these two transformations, one called T1, transformation 1 from domain U to codomain V. These are vector spaces U, V, and W over here. And I have another transformation T2, right, transformation 2 from vector space V, domain V, to codomain W. And suppose that both of these are linear transformations. Okay, so both of them would satisfy additivity property and homogeneity property. Then the composition of T2 with T1 is the linear transformation, and this is something you can show. You could actually go through and show that this rule I'm writing here does satisfy the additivity property and homogeneity property of a linear transformation if both T1 and T2 are linear, but I'll leave that to you to read or show on your own. So the composition of T2 with T1 is the linear transformation denoted by this. It's T2 with composed with T1. T2 and a little O symbol, a little circle between them. And then T1, just like I said back in algebra class, pre-calculus, calculus, when you see this little O symbol between two transformation names or function names, it meant you're doing composition. So T2 composed with T1 would have a domain of U and a codomain of W, right? And that's the same U and W as up top here. Because what's going to be happening is we're going to start off with a vector from U, and we're going to go through transformation T1 first, right? The right one here, T1. Go through that first from a vector, take a vector from U, take me to a vector in V, and then we're going to take that vector in V and go through transformation T2, which will take that vector from V and output me a vector in W. That's why my input's coming from U in this composition and the output's coming from W. And the way it's defined, the rule that defines a composition, is this transformation T2 composed with T1 takes a vector U from U, and the output is the value of T2 at T1 of U. Right, so again, this kind of describes, like I said earlier, what's happening. It's I take vector u, some vector from the domain u. I plug it into transformation T1. That'll give me a vector from V, right? The codomain of T1. And then if this vector is in the domain of T2, then I can keep going, plug this vector into T2 and give me an output from W. Alright, so keep this in mind, so I put a little box here, that's going to be important. Alright, we've got a little diagram showing the same thing I just talked about. Here's a little diagram about transformation composition. So imagine these circles just represent the vector spaces u, v, and w. What's happening in composition is this, as I said. You take vector from u, I pass it through, I apply transformation T1 to this to get the image T1 of u, and that would belong to v. And then I would take the image, that vector from v, T1 of u, and then apply T2, apply transformation T2 to this vector T1 of u, giving me T2 of T1 of u. But that is the same thing as just simply taking vector u and applying transformation called T2 composed with T1 to this vector u. Get T2 composed with T1 of u. So these mean the same thing. All right, one thing to point out here. If the range of T1, right, if the range of T1, if the range of the first transformation you apply, because I could switch the order here that you're going to see. So again, just the one on the right is the first one you're going to apply. If the range of T1 is not part of the domain of T2, right? If the range of T1 is not contained in the domain of T2, then the function composition T2 composed with T1 would not be well defined. Then T2 composed with T1 is not well defined. All right, and what do I mean by this? All right. So again, remember every vector from the domain, every vector from U is going to get sent to some range, right? So say this is, remember the range is not always the codomain. So say this is the range here, the range of T1, this orange circle inside V. If for some reason you map to a vector that wasn't in V, or if you got a vector outside of V, then you couldn't plug into T2. Right? You couldn't get an output through T2. So the range of the first transformation has to be contained within the codomain of the first transformation, or again, the codomain of the first transformation is the domain of the second one. Right. So yeah, like I said, if for some reason this vector got mapped to some vector that wasn't inside V, right, then I couldn't plug this into T2 because it wasn't part of the domain of T2. Right. So this is kind of important to remember, right? And for this reason, right, for the statement I just mentioned down here, you're going to see that the order in which you compose transformations will matter. So you're going to see that T2 composed with T1 in a lot of cases is going to be very different than T1 composed with T2, right, if I just switch the order. Alright, so hopefully that makes sense what's going on though, right, how you perform composition. Let's take a look at it in action. Alright, so here's an example. Next, I just have the two examples with pairs of transformations, linear transformations. Okay, so suppose we're given these, linear transformations. We've got transformation 1, which is T1, and transformation 2, T2. Now T1 has a domain of R2 and a codomain of R3. And T1 of, some vector from R2 goes to some vector from R3, like this, right? Just look at the symbols. T2, has a domain of R3 and a codomain of R2, and T2 sends a vector from R3 into this vector from R2. And again, just read over the symbols. All right. So first I'm asked, I got two of these parts here. First I'm asked to find, what's the image of vector 2, negative 1 under the composite transformation, T2 composed with T1. Right. Now there are actually two methods for this. You can do this in two different ways. Right, so the first, let me keep that up there. So the first method, call this method 1. Let's actually, instead of plugging in a specific vector to T2 composed with T1, let's find what that transformation is in general, T2 composed with T1. So find T2 composed with T1 when the input is, any vector from R2, right, xy. Right. So I'm hoping you are seeing that T2 composed with T1 would have a domain of R2, because again, I'm going into, again, the one on the right is the first one you enter, and then you enter the next transformation. So I'm applying T1 first, meaning I'm starting with vectors from R2, and where I would end, right, the codomain of T2 composed with T1. Well, if I go through T1, that takes me from a vector in R2 to a vector in R3. And then I'd go to T2. Well, look, R3, right, the codomain of T1 is, those vectors are in the domain of T2. So this will be well defined, right? That was what I was saying in the last page. Right? If the output vectors of the first transformation aren't in the domain of the second transformation, you can't go any further. But here we can. So I go through T1, get an output from R3, then I would take that output and put it through T2, which would give me an output in R2. So I'd be starting the composition with a vector from R2 and ending the composition with a vector from R2. So this is this is going to be a linear transformation from R2 to R2. And here's how it looks, right? So I would take T2 composed with T1, and again, I'm just starting off with some vector from R2 general, say xy, or you could call it x1, x2 if you want, a, b, whatever, as long as you have a vector with two generic components that represent real numbers. So remember how this is defined. This was on the previous page. This is, I take what's T2 at T1 of xy. Right, so this is telling me take the vector from R2, apply T1 to it, then take that vector, whatever that is, and apply T2 to it. All right. So again, here's T1 and T2. So I'm going to take xy and apply T1. So instead of x1 and x2, I have x and y. So everywhere there's an x1, replace it with x. Everywhere there's an x2, replace it with y. So this is equal to T2 at, all right, and then this t1 of xy, I'm going to put in here. Now it's going to, when I plug in xy to t1, it's going to give me an output that's 3 components. So I got this vector with 3 components in here. x1 plus 2x2. So x plus 2y as the first component. x1 minus x2, so x minus y as the second component. And then 3x1, so just 3x as the third component. Alright, and then I take that output, and it is a vector from R3. So like I said, I can apply T2, right? This vector would be in the domain of T2, so I can keep going. Then I apply T2 to this vector. Now, here's the rule for T2. Now again, instead of x1, x2, and x3, my input is x plus 2y, x minus y, 3x. So everywhere there's an x1, here and here, I'm going to replace it with the quantity x plus 2y. And everywhere there's an x2, I'm going to replace it with the quantity x minus y. And everywhere there's an x3, I'm going to replace it with 3 times x. Alright, so I apply T2 to this vector with 3 components here, and the output is again from R2 in T2. So I get this vector with 2 components. So x1, that's this x plus 2y, right, that's x1, minus x2, so minus the quantity x minus y, and then plus x3, so plus 3x. Alright, and I'll simplify that in a second, combining like terms and whatnot, the x's and y's. Alright, then the second component in the outputs of T2 is 3 times x1, 3 times the first component, so 3 times the quantity x plus 2y, and then minus 5 times the third component, so minus 5 times the 3x. Alright, and then we'll simplify this. Alright, so the value of T2 composed with T1 at some input from R2, right, from the domain xy, will be equal to, and again, the outputs of this composition, this composite transformation, is also from R2. And let's see, if I have x minus x plus 3x, that's just 3x. And then still with the first, I combine the x terms. Now the y's, you have 2y minus negative y. That'd be 2y plus y. And those are the only y's, so plus 3y. So 3x plus 3y for the first component of the output of this composite function, this composition. And then down here, we have 3x minus 15x, so it'll be negative 12x. And then plus 6y would be the only y term there. So I'll put this in a little box, right? This is the rule for the composite function T2 composed with T1. Right, when T2 and T1 are these rules here, these transformations here. Okay, and then plug in the specific number, right, the specific vector that we were given. Right, we were asked to find this. Right, we were asked to find what's T2 composed with T1. What's the value of this transformation at the input of the vector 2, negative 1. So I'm just replacing x with 2 and y with negative 1 down here. So T2 composed with T1 at this vector 2, negative 1 would be equal to the vector with components 3 times x, so 3 times 2, plus 3 times y, 3 times negative 1 for the first component, and I'll simplify that in a second. And the second component, negative 12 times x, negative 12 times 2, plus 6 times y, 6 times negative 1 for the second component. And then simplifying these, 6 plus negative 3 is 3, and then negative 24 minus 6, negative 30. This would be what was being asked for, right? This vector 3, negative 30, I'll put that up here as well, it's 3, the vector 3, negative 30 from R2, right, with 2 components. All right, so that would be one way to go about it. And now that I have this general rule, all right, now that I have the general rule written out, I can plug in, any specific vector I wish from R2 and get another output from R2, all right, instead of just this specific one, right? I can plug in other ones. Now the other method is just to work one step at a time with the vector that you're given, all right? So let's call this, I'll call this method 2. So again, same rules up here, same transformations. So same problem, and again, it doesn't matter to me which way you decide to do it. It'll end up with the same thing. All right, so I'm trying to find T2 composed with T1, and the value of this new composite transformation when the input is to -1. All right, again, remember how this is defined. This tells me to take T2 at T1 at the vector 2, -1. Lots of parentheses and brackets, I know. So I take the vector 2, -1, and I apply transformation 1 first. All right, I apply transformation 1 first. All right, let's take this over here. What's transformation 1? It's this. So instead of x1, x2, I have 2 and -1, right, applying transformation 1. So this results in T2, haven't done that yet, so I still write it, of, and then when I apply T1 to this vector, I'm getting a vector with 3 components. Probably should have had the arrow actually point to it. There you go. A vector with 3 components where you have 2 plus, again, x1 is 2, x2 is -1. So 2 plus 2 times -1, 2 plus -2, or 0 for the first component. Then 2 minus -1, 2 plus 1, that'd be 3 for the second component. And then 3 times 2, 6 for the third component. All right, so now I take this output, this 0, 3, 6 that I got after applying T1 to the vector 2, -1, and then I apply the transformation T2. All right, which again I can, because this vector, this input vector, is in the domain of T2, so it's okay, I can keep going. If it's not, then I would stop and say it's not well defined, right, or not defined. All right, so now instead of x1, x2, x3, I have 0, 3, 6. And I get some vector with 2 components. So 0 minus 3 plus 6. 0 minus 3 plus 6. That's just 3 for the first component. And then 3 times 0 is 0. And then minus 5 times 6 is -30. And there we go. The image of 2, -1 under this composite transformation, this composition to T2 composed with T1, is the vector 3, -30. And that is exactly what I got earlier doing it, the lawn way, where I found T2 composed with T1 at xy and then just plugged in 2 for x and -1 for y when I was all done. Yeah, same thing, same result. Okay, so part B, right, same transformations, okay, same 2 transformations, T1 and T2 here, from R2 to R3 and R3 to R2. But this time, I'm going to compose in the other order, right? So far, all I've seen is T2 composed with T1. Well, what about the other way around? Here's part B. How about it? What if they asked me to find, what's the image of this vector with 3 components, 1, 0, -3, under the transformation T1 composed with T2, this composite transformation? You see how the order has changed. So now the first transformation I'm going to apply is T2, right, the one on the right. And then after I apply T2 and get an output, I'm going to take that output and then apply T1. And let's see if we even can though, right? Because what's going to happen here? All right, so I've got this vector from R3, which is in the domain of T2, right? I plug it into T2, that'll give me a vector from R2. And then can I take a vector from R2 and then apply T1? Yes, because any vector from R2 is going to be in the domain of T1, so I can continue. All right. Just remember the domain of the codomain of the first function has to be the same as the domain of the next function over, right? Or the first transformation, the next transformation. All right. So again, that first method, I'll do it both ways again here. Method 1. I'm going to find in general, instead of, what's T1 composed with T2 at, this specific vector from R3, just take any vector from R3, and then when we're done, I'm going to plug in, 1 for x, 0 for y, and -3 for z. Right. So again, you could use x1, x2, x3 if you want. I'm just x, y, z, a, b, c, whatever. Right? Just something with 3 components that represent any real number here. All right, so let's do this. So remember how this is again defined. This would be, you're taking T1 at the value of T2 at this input x, y, z. All right, so the first thing being done here is we're applying T2. So there's the rule for T2. We're applying T2 first to the vector x, y, z, right? So instead of x1, x2, x3, just make it I'm making it x, y, z now. All right, so take this over here and actually put the output beneath the arrow this time. So what is the output here? All right, well, if I remember, I'm getting a vector from R2, right? So this will be 2 components. First component will just be x minus y plus z. And then the second component will be 3x minus 5z. And then we're applying T1 to this, right? So I plug x, y, z into T2, gives me this output. And then I take this output, which is from R2, and apply T1 to it. And I can, because the domain of T1 is R2, right? This vector in here, in the parentheses, is in the domain of T1, so I can keep using it. All right, and then I apply T1. Now remember, T1 goes from R2 to R3. Now instead of x1, right, everywhere there's an x1, so here and here and here, everywhere there's an x1, I'm going to replace it with the quantity x, y minus y plus z, right, that first component of this input vector here. And everywhere there's an x2, I'm going to replace it with 3x minus 5z, that quantity. All right, so I apply now T1 to this vector, and it gives me a vector with 3 components, which will simplify, of course, following this rule. So I have x1, so x minus y plus z, plus 2x2, so plus 2 times the quantity 3x minus 5z. All right, well, like I said, we'll simplify, combine like terms in that in a second. And then the next component, x1 minus x2, so x1, again, x minus y plus z, minus x2, the quantity 3x minus 5z, and then 3 times x1, so 3 times this quantity x minus y plus z. And then we'll simplify this. So this is 3 components. The first one, the x's, you have x here, then distributing the 2, you'd have plus 6x, that's 7x. Then the y's, you have negative y here, there's no y over there, so minus y. And the z's, you got z here, minus 10z, so minus 9z. And there's your first component when it's all simplified. Then second component, x minus 3x, negative 2x, negative y, no more y's, so minus y again. Z plus 5z, right, distributing the negative is plus 6z. And then the bottom, you're just distributing the 3, 3x minus 3y plus 3z. And there you go. This is the value. I've applied both t2 and then t1. Right? So this is t1 composed with t2 at any vector from R3, x, y, z. And I'll put this in a little box. Right? Now, do you notice how when I did this for part A, when I did the other order, when I did t2 composed with t1, you see how t2 composed with t1, that transformation was totally different, right? Because this transformation goes from R2 to R2. Do you see how T1 composed with T2 here? Maybe I'll write it up here. T1 composed with T2 goes from R3 to R3, right? My input's a vector with 3 components. My output is a vector with 3 components, and real number components. Totally different domain, totally different codomain. So that tells you something very important. Transformations are not commutative under composition. All right, and I'll write that on the next page, right? All right, so transformations, and again, it's a big thing because people often they just want things to be true so badly they don't really realize what they're looking at. Transformations are not commutative under composition. Because you just saw, T2 composed with T1 is not necessarily or not always going to be equal to T1 composed with T2. Okay, you can't, right? Yeah, again, when I say not commutative, that just means you can't just switch the order and have it be the same thing, because it won't always. There are some cases when they are equal, but not all. All right, so just know that you can't just switch the order of composition in general. All right, so now back to the problem at hand, right? So I went through and I found T1 composed with T2 at any vector from R3 as the input. Now I'm just going to go to this specific one, replace x with 1, y with 0, z with -3. So we have T1 composed with T2 at any vector. So T1 composed with T2 at the vector 1, 0, -3, like I was asked for, is just go through this thing here, replace all the x's with 1, y's with 0s, and z's with -3. All right, I'm just going to say it out loud. I mean, you can do simple arithmetic here. 7 times 1, 7. The y's are gone, right? Y is 0, 0, 0 there, so I'm not even going to worry about the y terms. So 7 times 1, 7. And then -9 times -3 is +27. So 7 and +27 make 34 for the first component. Then -2 times 1, -2. 6 times -3 is -18. -2, -18 combined make -20 for the second component. And then third component, 3 times 1, right? 3. Then 3 times -3 is -9. 3 and -9 combined make -6. So here we go. This is the image of the vector 1, 0, -3 under this composite transformation called T1 composed with T2. All right, so that was method 1. Again, you find in general what happens, and then you plug in specific numbers, specific vectors. The other way around, not the other way around, but the other way, All right, method 2 was just to use that specific vector from the beginning. So if I want T1 compose with T2 at the vector 1, 0, negative 3, I just, again, remember how this is defined. This is what is T1 at T2 at the vector 1, 0, 3, negative 3, 1, 1, 0, negative 3. Right. And then I do this first, right? You apply T2 first. Right. So if I do that, let's go back to the rule for T2, right, way back here. So there's the rule for T2. And again, I'm replacing x1, x2, and x3 with 1, 0, and negative 3. Right, so that'll give me an output that's a vector with two components, and then I'm going to apply T1 to it. All right. So we have what? 1, again, the x2 is 0, so I'm not worried about x2. So 1 plus negative 3 is negative 2 for the first component. That's probably too big a set of parentheses here. Sorry. All right, and then the next one, 3 times 1, and then plus negative 5 times negative 3 is 15. 3 plus 15, 18. Right. Then I take this output, negative 218 here, and then apply the next function over, right, transformation over, sorry, and then T1. So what was the rule for T1? That's this here. All right, going back again, instead of x1 and x2, I have negative 2 and 18. And we finally get this, with 3 components as an output here. So I'll have three components. Come on. All right. So again, this is negative 2 plus 2 times 18 is 36. Negative 2 plus 36 is 34 for the first component. Hey, look at that. That matches the one I got earlier. It should. Right? These should be equal. Then negative 2 plus minus 18 is negative 20. Great. Matches the second one I got earlier. And then 3 times negative 2 is negative 6. And look, that's exactly the same output I got earlier when I found it in general for some general vector x, y, z, and then plugged in 1, 0, negative 3. So you can do either way when you're asked to evaluate a composition at a specific vector. All right, so that example there involved a couple transformations between Euclidean spaces, right? R2, R3, R4, R5, etc. Where the vectors were written as just column vectors, like typical. And my next example has a couple linear transformations, between some non-Euclidean vector spaces. All right, so here we're given linear transformations. T1 is a transformation from P1, right? This is the set of all polynomials of degree 1 or less, to R2 by 2, and remember this is the set of all matrices, 2 by 2 matrices with real entries. And the rule does this. It takes a polynomial of degree 1 or less, which all look like this, a plus bx, and sends it to this 2 by 2 matrix with a, b, and then 2a and 3b as the entries. Right? And a and b are assumed to be real numbers here. Then T2 is got a domain of the complex numbers and the codomain of P1. And it sends a complex number, a plus bi. Remember that I is the imaginary unit, the square root of negative 1, and a and b are real numbers. Right? So you have a real number plus some imaginary number here. A real number times I. Sends a complex number, a plus bi, to this, the output's going to be a polynomial of degree 1 or less, b minus ax. All right, so what we're asked for in the first problem. Again, I'll do it both ways. All right. So I'm asked to find what's the value of this transformation, the image of the under this transformation of the vector or the number 3 minus 5i. I have t1 composed with t2, right, in this order. So what I'm going to do is I'm going to apply t2 first, then take whatever that output is and apply t1. Well, first let's see if we even can, right? If you plug a complex number into t2, well, first you can do that because the domain of t2 is the complex numbers. See, the output is going to be a polynomial of degree 1 or less. And then I take that output, whatever this is, and I plug it into t1. Can I do that? Well, yes. See how the codomain of t2 is the same as the domain of t1. So when I get an output from t2, I can plug it in to t1 because it's part of the domain. So this is totally a valid expression I have here. All right. So, like before, method 1 is I just find the general expression. Let's find what's t1 composed with t2 at, instead of 3 minus 5i, at just some general complex number, a plus bi, where a and b are real, right? And I is that imaginary unit. All right, so remember what this is, how this is defined. This is what's t1 at t2 at a plus bi. And I apply transformation 2 first this time. All right. So this is going to be t1 of, and I'm putting this out, whatever this output is, in here. Right. So I apply t2. Oops, I forgot to put the numbers t1, t2 up here. My bad. So what's t2 applied to a plus bi? Well, it's exactly the same as this here. I got a plus bi plus, so it's b minus ax. B minus ax. All right, now be careful with the, just because I got a bunch of a's and b's here, you got to pay attention to how things are positioned. All right, because now what I'm going to do is I'm going to take this polynomial. This is a polynomial of degree 1 or less. If a is 0, it's less, but b minus a times x, and plug this into t1. Let's look at transformation t1. So I know this is going to look a little weird, but you got to get used to this, right? You got to pay attention to positions of things, not necessarily the letters that are being used. Let's look at what t1 does. You have a constant plus a number times x. The constant term goes here and here. The coefficient of x goes here and here in the output. So my output's going to be a 2 by 2 matrix. And again, I know this says a, but what's the constant term in this polynomial? My input for t1 down here is b. So instead of a, I'm using b. So everywhere there's an a up here in the original rule, I'm now using b because that's the constant term now. So instead of a, it's b. And there, instead of 2a, that'll be 2b. Right. Okay? And then the coefficient of x in the original rule is, positive b here. But what's the coefficient of x in my input here? It's negative a. So instead of b, I'm going to replace all the b's up in the original rule, so the b here, the b here. I'm going to replace all the b's with minus a. So that b becomes minus a. And 3 times b becomes 3 times minus a, which would be minus 3a. Again, I know it can be a bit confusing if people are using the same letters for things, but you really just got to pay attention to positions of stuff. What are the constant terms? What is the coefficient of x? Where do those go in this matrix? And put these down here in the exact same positions. Pay attention to positions. All right, there we go. And then I've done both, right? I've applied T2 to a plus bi, and then I applied T1 to b minus ax, giving me my final output. So this here is T1 composed with T2 at any complex number at a plus bi. All right, so now all I need to do is apply this rule. All right, here's the rule now for T1 composed with T2 at some complex number a plus bi. Gives me this output, this 2 by 2 matrix. Apply this rule to this specific complex number. So you see how a is positive 3, and b, the number times I, b is negative 5. So I replace all the a's with positive 3, all the b's with negative 5, and we'd get the following. So T1 composed with T2 at 3 minus 5i is equal to the 2 by 2 matrix, where again b is the coefficient of I, right? So negative 5. And then minus a, so the opposite of the constant, the opposite of the real part, the real number on its own without I. So negative 3, right? The opposite of a, opposite of 3, a is 3 here. And then again, replacing b with negative 5, this is negative 10, right? 2 times negative 5. And replacing a again with 3, negative 3 times 3 is negative 9. All right, so this is the final output here. All right, so the image of 3 minus 5i under this composite transformation T1 composed with T2 is this 2 by 2 matrix with rows negative 5, negative 3, and negative 10, negative 9. All right, so that was again the long way, I guess, of going about it. Now the other way would be just to use the specific complex number you have and apply the transformations one at a time. So again, this is method 2. All right, so I've got T1 composed with T2 at 3 minus 5i. And just remember how it's defined, right? This would be T1 of T2 of 3 minus 5i. And I'm applying T2 first, which I have right up here. So again, a, instead of a plus bi, right, as my input for T2, I have 3 minus 5i. So a is 3, b is negative 5. So this is equal to T1 of, and we're putting, this value of T2, we're putting this output in here. And again, I just replace a with 3, b with negative 5. So it'd be negative 5 at the b, then minus 3 times x. Replacing a with 3, b with negative 5. All right. So I got my polynomial of degree 1 or less, it's degree 1 here now. And then I plug it into T1, right? I apply T1. Right? So let's go look at what T1 does to a polynomial. So there's transformation 1, T1. And instead of a plus bx being input, it's negative 5 minus 3x. So a I replace with negative 5, b I replace with negative 3. And the output will be, a negative 5. 2 times a, 2 times negative 5, negative 10. B, I said, was negative 3, so negative 3, and then 3 times negative 3, negative 9. And there you go. We applied both transformations, right? We have finished the composition, and that's it, right? And just look, right? That is exactly the same thing I got earlier, right? The same two matrices with the same entries in the same positions. So you do either order you wish, right? Find the general transformation and then plug in specific values, or just keep those specific values and work through the composition one at a time, right? Work through each transformation one at a time. Now, so far, I've only done a composition of 2 transformations. Just know that you could see, I'm not going to do it here, but you could see more than 2. they could ask for this here, well, maybe not for this example, but I could say what's, T1 composed with T2 composed with T3 or something. I mean, you could see of some vector x. I mean, you can see more than one transformation being composed. Just remember, you're just going in this order. Plug this into T3, then plug that result into T2, then plug that result into T1 if possible. All right, just kind of going right to left here. Or you could also think of it as going inside out, if you write it the way with all the parentheses and brackets that I had. All right, so just know that, even though I'm only doing examples with two of them, two transformations being composed, just know that you can compose more than two transformations if necessary. All right, so let's keep these. All right, so the same two transformations still. And my second part to this is, T1, T2 here, same definitions. But now I'm asked, what's T2 composed with T1 of 4 plus 7x? Again, another way I could write this, T2 of T1 of 4 plus 7x. Lots of parentheses. Now the question here is, first of all, can I even do it? All right, is it even well defined? Because look, what happens when I plug this in? When I take 4 plus 7x and apply transformation 1, this is a vector from R 2 by 2, isn't it? If I apply transformation 1, it takes my polynomial of degree 1, which I have here or less, and gives me an output that's a 2 by 2 matrix. Can I plug a 2 by 2 matrix into transformation 2? No, I can't. Transformation 2's domain is the complex numbers, not a set of 2 by 2 matrices. So this vector, this whatever T1 of 4 plus 7x is, this is not in the domain of T2. So I cannot keep going. I cannot continue. Therefore, all I would need to say is that this thing here, what I'm being asked for, what's T2 composed with T1 at 4 plus 7x, this is not defined or not well defined. This transformation would not be well defined is what they'd say. Not defined, and I am done, right? There's nothing to do there. I mean, you could plug this in and get some matrix, but then you'd realize hopefully really quickly that you couldn't plug the matrix into T2. Okay. Alright, so that was a bunch of evaluating. Alright, finding the outputs of some function transformation compositions. In the last part of the video here, maybe the last, 20 minutes, we'll see. I want to talk about the one-to-oneness and onto-ness of composite functions, compositions. What conditions guarantee that the function, the composite transformation will be one-to-one? What conditions guarantee that a composite transformation will be onto? All right, and I'm not going to go over how to determine if a transformation is one-to-one and onto again. I'm not doing that. That has been done in several videos now. I'm just assuming here that you know what it means for a transformation to be one-to-one, a transformation to be onto. All right. So let's talk about one-to-oneness or injectiveness of a transformation. So there's going to be a lot of writing and drawings the rest of the way. Hope it makes sense to you. So here, the composition of one-to-one linear transformations will also be a one-to-one linear transformation. So that's saying that if I have two linear transformations, say T1 and T2, and they are both one-to-one, So this is a one-to-one transformation, and this is a one-to-one transformation. If you know that already, then their composition, T2 composed with T1, as long as it's well defined, which this would be, right, just looking at the domains and codomains, then their composition will also be one-to-one. Right, so here are some conditions that will guarantee that a composite transformation will be one-to-one. If the two transformations you're using to make the composition are also one-to-one, then the composition will be one-to-one itself. Right. Now another way to think about this is by doing the contrapositive of this statement. This is if something, then something. The contrapositive is you take the second statement, negate it, the first statement, negate it, and then switch them. Okay, so if a composite function is not one-to-one, then either one of them, at least one of them has to be not one-to-one either also. Right. If a composite function is not one-to-one, then T2 could not be one-to-one, or T1 could not be one-to-one, or both of them could not be one-to-one. Right, and I've shown you a picture like that. Right. Now this is a very simple picture, right, with just a few elements from, say, again, these vectors. Say these vector spaces U, V, and W here. So there's a diagram demonstrating that second statement. All right, the second. So if I have a composite function that I know is not one-to-one, then that means at least one of the transformations I use to make it must not be one-to-one either. Right. So here, say I got vector space U, V, and W, and again, there's just a few, just 3 vectors in this one, 3 vectors in this one, 4 vectors in this one. Okay, and going from U to V, that's transformation 1. From V to W, that's transformation 2. And then from U to W, that's the composite, that's T2 composed with T1. Right. So here's transformation T1, right? It sends U1 to V2, U2 to V1, U3 to V2. So can you see that T1 is not one-to-one? If I ignore all this, get rid of T2 there. See, it's not one-to-one because there are 2 different inputs that go to the same output. All right, let's just keep that in mind. And then T2 takes V1 to W1, V2 to W2, and V3 to W4. All right. And again, ignore this, and you can see that this is a one-to-one function, right? There aren't 2 different inputs going to the same output. So T1's not one-to-one, T2 is one-to-one, but it doesn't matter. What I'm trying to say is, if you know the composite function is not one-to-one, then one of them has to be not one-to-one. So let's look. Is the function from U to W one-to-one? Let's see. U1 goes to W2. U2 goes to W1. So far so good. 2 different inputs going to different outputs. But U3 goes to W2 as well, right? So you see how U3 and U1, 2 different inputs in this composite function, go to the same output, W2, right? 2 different inputs go to the same output. So T2 composed with T1, the composite function is not one-to-one for that reason. And since we know the composite function is not one-to-one, then one of these has to be not one-to-one either, and we've seen that T1 is not one-to-one as well, right? Okay. So if you know so that, again, one more time. If you know a composite function, right, the final result, if you know that a composite function is not one-to-one, that means that at least one of the 2, I keep saying functions. I mean, transformations are like a generalization of functions. So if I switch up transformations and functions, please know that they mean the same thing in this context. So if you know a composite function or a composite transformation is not one-to-one, that means that at least one of the functions that make it are not one-to-one either. Now you have to be careful with this. All right, let's go back to this statement again. So what I just showed you was a demonstration of the contrapositive of the statement. Right? If T1 and T2, if the two functions you're using are both one-to-one, and then you compose them, you'll get another one-to-one function transformation. And then I showed you the contrapositive of this statement, and demonstrated an example of that, the contrapositive. But be careful. Too often people confuse this with its converse. Now the converse of a statement is just you flip the hypothesis and conclusion. You flip the first statement and second statement. All right, so I'll write that here. Right, oh, actually, I got this right. It's right here on the next page. So be careful. All right, just because the statement I said originally was true, right? This was the statement's contrapositive. This statement I have here, if the composite function is one-to-one, then both T1 and T2 are one-to-one. That's just reversing these two statements, right? This is if both T1 and T2 are one-to-one, then T2 composed with T1 is also one-to-one. Just switch that, and you get this statement. If the composition is one-to-one, then both of these are one-to-one. That is called the converse, right, where you just switch the statements. And this is not necessarily true. All right. Again, just like I said, this does not mean that this is true. Let's see that, right? Look at this. So suppose we have a composition that's one-to-one, like this here. Again, very simple picture with just a couple vectors in U, a few vectors in V, two vectors in W. Let's say again, U to V here is transformation 1, V to W is transformation 2, and then U to W is T2 composed with T1, the composition. Now look at T1 on its own. Is T1 one-to-one? Yes, it is, right? Two different inputs go to two different outputs. It's one-to-one. Look at T2. Is T2 one-to-one? No, it is not. Because you see, there are two different inputs, V2 and V3, that go to the same output, W2. So T2 is not one-to-one. But look at the composition. Look at from U to W. See how U1 goes to W1, U2 goes to W2. Different inputs are going to different outputs. So here we see the hypothesis is true, right? I have a composition that's one-to-one, but not both of the T2 and T1 are one-to-one, right? T2 is not one-to-one, but the composition is still one-to-one. So like, again, the converse of my original statement where I just switch them, that is not true. Do not believe that. All right? Cross it out. Get it out of your mind. All right? Because you can have a one-to-one composition where one of the functions that made the composition isn't one-to-one, like I'm showing you right here. All right? So just be careful. Only this direction. All right? So the only time you're guaranteed that a composition is one-to-one is if the two transformations that make the composition, if you know that those are one-to-one as well. That's the only time you're really guaranteed that the composition function will be one-to-one. Right, and then very similarly, right, in a very similar fashion, I can say the same thing about the word onto. Right, when a function is onto. Okay, so same thing. The composition of two onto transformations is also going to be onto. All right, so again, this is if I have two transformations that are both onto. So if you know T1 and T2 are both onto, remember what onto means. Onto means that the range is equal to the codomain. That means every value, every vector in the codomain is mapped to. Right? So if the two if you know the two transformations you're using are both onto, then the composition will also be onto. So again, this is the only time you are guaranteed to know that a composition will be onto, is if the two transformations you use to make the composition are both onto as well. This is also equivalent to the contrapositive, right? Again, where I just take the two statements, the one after if and the one after then, I make them, I do not them, I negate them, and then switch them. So if a composition, T2 composed with T1, if a composition is not onto, then T1 and T2 are not both onto, meaning at least one of them is not onto. All right, so if you have a composition that you know is not onto, not surjective, then you'll know that at least one of the two functions that make it can't be onto either. All right, so here's a picture demonstrating that. Just again, a very simple picture with just very few vectors. So again, imagine these are vector spaces U, V, W. So again, U to V is T1, V to W is T2, and then U to W is the composition T2 to T2 composed of T1. Now look at T1. T1 is onto. Right. Every vector in V is mapped to. T2, right, if you look at T2 separately, right, V to W, that is not onto, because there is a vector in W that doesn't get mapped to. Right? There's a vector in W that is not in the range. But look at this. So look at the composition. You know, U1 goes to W1, U2 goes to W2. Again, still obviously, the composition from U to W is not onto. Right? It's not onto. And because it's not onto, right? Because I know the composition is not onto, at least one of the two functions that make it must not be onto either. And you can see again that T2 is not onto. Right? So that's what I was saying here. If you know a composition is not onto, if you have shown that a composite function is not onto, then at least one of the two functions that made it must not be onto either. Now, just like before, just like with the one-to-one talk, the converse of this first statement, the converse of this is not true. This is true, but if you just switch the if-then, you know, you switch the statement after if with the statement after then, it's not true. And that's what I have here. All right, again, be very careful. Again, this statement I have in the box here is the converse, where I just switch the statements. Right? So the first statement, the true statement, was if T1 and T2 are onto, both onto, then the composition will be onto as well. The reverse of that, the converse of that, would be if the composition is onto, then T1 and T2 will be onto. If the composition is onto, then both T1 and T2 are onto. That is not true. And I'll show you here. Here's a picture of two functions being composed, again, just like before, U, V, W, and then T1's from U to V, T2's from V to W, and T2 composed of T1 is from U to W. This composition is onto. Look, see how, U1 goes to W1 in the composition, and U2 goes to W2 in the composition. So the range of the composite function is all of W, right? Everything in W, both of these vectors, all the vectors in W are mapped to under the composition. So this part's true. You got the hypothesis is true, but is the conclusion true? Here I have a composition that's onto. This is an onto composition. But does that mean that the functions that made them are both onto as well? Well, look at T1 from U to V. U goes to V2, U2 goes to V1. V3 is not hit. T1, transformation 1 here, is not onto. Now V2, T2 is, right? Because, for V to W, everything in W is hit. Right? T2 is onto, but T1 is not onto. So just because a composition is onto doesn't mean that the two functions that made them are onto. You'd have to check. All right, so going back to the original statement, right? This is the only time you are guaranteed that a composition will be onto and not have to check. Right? If the two functions you are using, if you know they're onto, you can show they're onto, then the composite will be onto also, and you don't need to show that. All right. But if one of them's onto and the other one's not, then you say, oh, well, then the composition may or may not be, right? Just like for one-to-one. If one of them's one-to-one and the other one is not, the composition might be one-to-one, but it also might not be. You'd have to check in those cases. You're not guaranteed anything. You're only guaranteed one-to-oneness and onto-ness if both the transformations you're using to make the composition are both one-to-one. The composition will be one-to-one. If they're both onto, the composition will be onto. I know I'm repeating myself a lot, but I just want to make that hopefully perfectly clear, because I see people make too many mistakes, thinking that the converse is true. All right, so I hope that made some sense. And again, I'm not going to go into how to show that a transformation is one-to-one, or how to show that transformation is onto. That was in a prior video. I've done that several times, in several videos now, actually, quite a bit. So I just wanted to talk about the relationship between a composite function and the transformations that make it up. All right. So I hope you enjoy evaluating composite functions, composite transformations, and also determining whether or not a composite transformation is one-to-one or a composite transformation is onto. And thank you very much for watching.